Let me welcome you to this lecture. We have now discussed about a very important class of compound formed by carbon. That is, we have discussed about carbides, and during this lecture we will discuss about another important class of compound of carbon, that is oxides of carbon. Now there are several oxides of carbon known. Two of them are very well known and they are very stable oxides of carbon, that is carbon monoxide and carbon dioxide. So these two oxides of carbon are pretty well known and these are stable oxides of carbon. Apart from these two oxides of carbon, there are other oxides of carbon are also known, and these are unstable or less stable oxides of carbon. Examples are C3O2, that is carbon suboxide, one can call it C5O2 and C12O9. So these are less stable oxides of carbon. Now there is one important difference of the oxide of carbon with the oxides of other group 14 element. That is, these oxides of carbon, they are all molecular species. These are molecular species. So carbon dioxide is a gas, again carbon monoxide is also a gas, and these compounds are as well again gases, and these gases, these are essentially molecular species, or each there are molecules of carbon dioxide and molecules of carbon monoxide, so and so. But the other oxides of carbon, so group 14 elements, that is, say for example, the oxide of silicon, germanium, tin or lead, they are not these are not molecular species. These oxides are not molecular species, but these are oxides are extended solids. So for example, oxide of silicon, SiO2, we know is a solid which melts at very high temperature, and this is not a molecular species because there are connections between these oxygen atoms are again, you know, this is three-dimensional polymeric structure it has, the silica, where the oxygen atoms are connected to silicon atoms throughout the extended solid. So that is why this is not it is not a molecular species, but it's an extended solid, we call. The reason for this difference in the oxides of carbon, while in case of carbon we see these are molecular species, but while the oxides of other group 14 element, they are non-molecular species, but they are extended solid, is because in case of carbon, the both the element in case of carbon, the when it forms compound with oxygen, both carbon and oxygen have a 2p and 2s orbital as the valence orbital. While in case of other oxides, in case of silicon, the valence orbital is 3p, 3s, while for germanium it is 4s, 4p, and this is for tin it is 5s, 5p, and for lead it is 6s, 6p. So when it forms linkage with oxygen, they cannot form these orbitals in these heavier elements cannot form p pi linkage with oxygen because of the difference in energy of the orbitals, while in case of carbon, because of the compatibility of the energy of the orbitals in carbon as well as in case of oxygen, there are p pi interactions, and because of these p pi interactions, the oxygen atoms are no longer connected to carbon atom of the nearby molecule, and that is why we have here molecular species formation, while in case of the other group 14 oxides, p pi linkages are absent because of the difference in energy between the orbitals of the group 14 element and the orbital of oxygen, and that is why we have formation of extended solids which have high melting points. So that is the difference in basic difference in the oxides of carbon with the oxides of other group 14 elements. So we will now discuss about the oxides of carbon, especially the chemistry of carbon monoxide and carbon dioxide in more detail. So let us discuss first with carbon monoxide. So carbon monoxide is a colorless, odorless, and it's a poisonous gas. And it is produced when one burns carbon in limited supply of oxygen. So this is the reason one should not make fire in a closed atmosphere, because in that case we will be consuming all the oxygen that is present in the closed environment, and eventually the concentration, as the concentration of oxygen decreases, carbon monoxide is going to be formed, and then because it is poisonous in nature, essentially it reduces the amount of oxygen in our body, and thereby what it does, it first makes us unconscious, and eventually the person is going to die because of carbon monoxide poisoning. So that is why one should be careful while making fire in closed environment. So then the laboratory method of preparation of carbon monoxide essentially involves again dehydration of formic acid by using concentrated H2SO4. So one can take formic acid, and when it is treated with concentrated H2SO4, dehydration of formic acid occurs, and this will eventually result in formation of carbon monoxide and water. So the carbon monoxide will be released as gas here, and uh, the carbon monoxide can be detected because it burns with blue flame, and also there are other analytical methods to detect carbon monoxide, because carbon monoxide can reduce palladium chloride into metallic palladium in aqueous medium, and that is why the metallic palladium, essentially its color is black. So once the palladium chloride solution turns into black metallic palladium, we will know that the atmosphere there is carbon monoxide is present. So the reaction involved is PdCl2, carbon monoxide in presence of water gives you metallic palladium. Carbon monoxide will get oxidized to carbon dioxide because palladium is reduced here from +2 to zero oxidation state. Carbon monoxide will get oxidized to carbon dioxide here, and HCl is also going to be there. So this is going to be 2 HCl, and the reaction is balanced in this way. So that is how carbon monoxide, the presence of carbon monoxide can be detected, because metallic palladium color is dark black. So from there we can find out, we can detect carbon monoxide. There is another reaction where carbon monoxide essentially reduces I2O5 into molecular iodine. So that is I2 plus CO2 once again, and in order to balance this reaction we can write it in this way. So now here this reaction can be used again as a tool to estimate the amount of carbon monoxide quantitatively, because the iodine that is produced in this reaction can be titrated with sodium thiosulfate, and that will essentially allow us to estimate the amount of carbon monoxide in a given system by doing iodometric titration here. So the carbon monoxide is a very important fuel, or is a component of many industrially important fuels, because carbon monoxide, when it is burned in air, it produces carbon dioxide, and the reaction or the enthalpy of this reaction is equal to minus 565 kilojoule per mole. So it is highly exothermic reaction, and because of this reason, carbon monoxide is a very it has importance as a fuel, and the industrially important fuels where carbon monoxide is a component are the water gas, that is a mixture of carbon monoxide and H2 is called water gas, and water gas can be prepared by passing steam through red hot coke. So you take red hot coke, which is carbon, and treat it with steam, then one can produce carbon monoxide plus H2. So that is your water gas, and the enthalpy of this reaction is plus 131 kilojoule per mole. So this reaction is endothermic in nature, and that is why the coke will essentially cool down after passing steam for some period, and that is why one needs to regularly, frequently stop the flow of steam and instead pass air to reheat the coke in this reaction. So then there is also another important industrial gas containing carbon monoxide as the component, that is called the producer gas, which is mixture of carbon monoxide with nitrogen, and producer gas can be prepared again by passing air through red hot coke. That is, one can take red hot coke again and pass air, which is oxygen and nitrogen in this ratio. So then one produces carbon dioxide, and this upon reaction with carbon once again will produce carbon monoxide, and this nitrogen is going to be there. So the overall reaction, it is carbon plus O2 giving us carbon monoxide. Essentially, for this reaction, the enthalpy of the reaction is equal to 221 kilojoule per mole, that is minus 221 kilojoule per mole. So this reaction is exothermic in nature, unlike the reaction which produces water gas, and that is why simply passing air through the red hot coke will eventually give us this producer gas as a fuel. Apart from water gas and producer gas, there is another industrially important fuel which contains carbon monoxide, that is coal gas, or it is also sometimes known as town gas, because it is prepared by or manufactured by distillation of coke, and it is a mixture of carbon monoxide, nitrogen, hydrogen, and CH4. So these four gases are present in this coal gas, and it is manufactured or produced by distillation of coal. Now, carbon monoxide is a very important ligand, and it forms complexes. Carbon monoxide as a ligand, it forms complexes with almost all the transition metals, and extensive chemistry of this carbonyl chemistry has been investigated, and one of the first compound which contained carbon monoxide as a ligand, which was prepared, was nickel tetracarbonyl, which was prepared or which is produced as part of Mond's process for purification of nickel, because nickel tetracarbonyl is a gas, and this allows one to purify nickel from other ores or metallic impurities, because the nickel reacts with carbon monoxide at room temperature itself, and this nickel carbonyl, which is a gaseous compound, can eventually be decomposed into nickel and carbon monoxide, once again giving us pure nickel. So apart from this nickel, almost all other transition metal also form binary as well as other metal carbonyl complexes, and the reason why carbon monoxide forms a stable metal carbonyl complexes can be understood if one looks at the molecular orbital diagram of carbon monoxide. So let us quickly draw the molecular orbital diagram of carbon monoxide. So that is, we have carbon, and then we have oxygen, and we have carbon monoxide. So let us try to draw the molecular orbital diagram of carbon monoxide. So here the configuration, the electronic configuration is 1s2, 2s2, 2p2 here, while in this case 1s2, 2s2, 2p4. So we will draw the molecular orbital diagram only for the valence electronic cell. So let us have the 2s here of carbon and 2s of oxygen. We will draw the 2s atomic orbital of oxygen at energy slightly lower than the energy of the 2s orbital of carbon, because oxygen is more electronegative element, and that is why the orbitals are more closer to the nucleus and their energies are much less than the energy of the corresponding orbital of carbon, which has less electronegativity. So then we can draw molecular orbitals formed by these 2s and 2s of carbon and 2s of oxygen, and then we have the atomic orbitals of carbon on this side and atomic orbitals of oxygen, that is 2p, and the 2p atomic orbitals of carbon and oxygen. And then we can draw first the sigma molecular orbitals and then the pi molecular orbitals in this fashion. Sorry, the sigma star is going to be here, and pi star is going to be somewhere over here. So the sequence of energy of these molecular orbitals are important. So let us fill electrons, 2s2, 2s2 here. In this case, 2 electrons into p orbital, and in this case, 4 electron into p orbital. So we will have 2 electrons in both here, sigma 2s bonding and sigma star 2s anti-bonding. This is pi 2p and sigma 2p, and this is pi star 2p, and this is sigma star 2p molecular orbital. And total we have 6 electrons in this 2p orbital of carbon and oxygen. So we will fill 6 electrons on that essentially fills up to sigma 2p bonding molecular orbital are occupied, and these pi star 2p and sigma star 2p molecular orbitals are essentially empty. So we term this particular molecular orbital as highest occupied molecular orbital or HOMO, while this molecular orbital we term it as LUMO, that is lowest unoccupied molecular orbital. So now when carbon monoxide acts as a ligand, it donates the electron pair in HOMO to empty metal orbitals, and that is how metal to carbon monoxide linkage is essentially formed. This is a sigma linkage we call, because this essentially is formed by a sigma type of molecular orbital and with a sigma molecular orbital or atomic orbital of the right symmetry of the metal. So this is how the sigma bond is formed, or the carbon monoxide to metal sigma bond is formed. Once this sigma bond is formed, because metal also have electrons, or the metals which form complexes with carbon monoxide are essentially in lower oxidation state, and that is why they are electron rich, and they can also donate electrons back to carbon monoxide. Now carbon monoxide does have a pair of orbitals where it can accept electrons from metal orbitals, and that is the LUMO, and when it forms complexes with metal, there is also metal can also donate electrons to the pi star 2p molecular orbital of carbon monoxide, and this is how another type of linkage is formed, that is a pi linkage. But in this linkage, electron density is transferred not from the ligand to the metal, but from the metal to the ligand, and that is why we term this sort of linkage as back bonding or pi back bonding. Sometimes it is called as, and that because here electron density is essentially transferred from the metal to carbon monoxide, and because of this pi back bonding, what essentially happens is that the carbon monoxide, because it receives electron density from the metal, it can now also act as a better sigma donor, and it increases the donation of electron from or sigma increases the strength of this sigma bond as well, because now carbon monoxide can act as a better sigma donor because it is accepting electron density from the metal, and thereby these two interactions essentially act cooperatively, and that is how carbon monoxide can now act as a very strong field donor or strong field ligand, and that is the reason why it forms stable complexes with metals in low oxidation state. That is also important because when metals are in high oxidation state, metal can no longer donate electrons to the 2pi star 2p molecular orbital of carbon monoxide, and that is why it can no longer again act as a good sigma donor, and therefore the interaction between metal and carbon monoxide is going to be poor, and the complexes formed are again going to be unstable in nature, and only with metals in low oxidation state carbon monoxide can form stable complexes, and the reason is obvious when we look at the molecular orbital diagram or the orbitals which are involved in bonding with metal. So you will learn more about the type of bonding or the nature of bonding, as well as the consequences of this pi back bonding in carbon monoxide metal complexes when we learn about organometallic chemistry, because this is part of organometallic chemistry. And instead we will now go ahead and discuss about other oxides of carbon. So the other important oxide of carbon, as we have already said, is carbon dioxide. The carbon dioxide is industrially prepared as a byproduct, or it is formed as it forms as a byproduct during the production of hydrogen gas, which is again industrially produced for preparation or manufacturing of ammonia by the Haber's process. That is the reaction between nitrogen and hydrogen gives us ammonia, and for this purpose one needs hydrogen, and when the industrial process or method for preparation of hydrogen essentially involves treating carbon monoxide with water at high temperature and pressure, and essentially it gives us carbon dioxide and H2. So this is a byproduct for formation during the production of H2 gas. So then another method or another important method where carbon dioxide is produced is during the fermentation process of sugars essentially. So what one takes C6H12O6 glucose, and if one does fermentation by using yeast, anaerobic fermentation, this essentially produces ethanol and carbon dioxide. So we can write 2 here, so that it will make this also 2. If we write, then the reaction gets balanced. So this is again an industrially important reaction, because this reaction is important for production of ethanol in breweries essentially. So another industrially important method for production of carbon dioxide is when one do calcination of limestone, which is calcium carbonate. So when it is heated or calcined, eventually one produces calcium oxide and carbon dioxide. So that is limestone. Now there are several important industrial application of carbon dioxide. The first and foremost industrial application of use of carbon dioxide is as a refrigerant, because carbon dioxide, the solid carbon dioxide, essentially acts as a refrigerant, and it is also known as dry ice. Now it has one important characteristic, that is it sublimes into a gaseous phase without converting into a the solid carbon dioxide essentially, or the dry ice gets it sublimes into gaseous state without converting into liquid phase, and the boiling point of this solid carbon dioxide is minus 78 degrees Celsius, and that is the reason why it is used as a refrigerant. Then apart from its application as a refrigerant, another industrially important application of carbon dioxide is during the production of urea, because carbon dioxide reacts with ammonia to give us ammonium carbonate, which is again, this is temperature of 180 degrees Celsius under pressure. It produces ammonium carbonate. And this again gives us eventually, because it is unstable, it gets transformed into urea, which is a very important fertilizer, and this is why again carbon dioxide is used industrially. Then apart from these two applications, there are other applications as well, that is carbon dioxide is used as a fire extinguisher, that we know. It is also used as aerosol propellant. So in case of perfumes, carbon dioxide is used as the propellant here. Then apart from that, it is also used to inflate, say, life jackets. So these are some of the other applications of carbon dioxide. Now if we look at the structure of carbon dioxide, or if we count the number of valence electron in carbon dioxide, we will find again that the number of electrons are exactly equal to the number of electrons in azide ion, and the structure of carbon dioxide is again linear, and this is the structure of carbon dioxide. Carbon atom is sp hybridized here, and so two of these sp hybridized lobes essentially form sigma bond with oxygen atom, or sp hybridized lobe of the oxygen atoms here, and then we will be left with two unhybridized perpendicular p orbitals here, which again carries one electron, because two electrons are used for formation of these sigma bonds with oxygen, and both of these two unorbital sp orbital contain one electron, and these are going to again form pi bonds with corresponding p orbitals of oxygen atom. So that is how we can look at the structure of carbon dioxide. It is a linear species because carbon atom is essentially sp hybridized, and again it is isoelectronic with azide. That also tells us that it is a linear compound. So then let us also look at the methods for detection of uh, carbon dioxide. One of the elementary method for detection of carbon dioxide is passing carbon dioxide gas through lime water, which is calcium hydroxide, and we know that it makes lime water cloudy because of the formation of calcium carbonate. Now, if we pass excess of lime water through excess of carbon dioxide gas through lime water, then what is going to happen is this calcium carbonate is going to react with carbon dioxide in this aqueous medium, and eventually it is going to form calcium bicarbonate, and this is a soluble species, and that is why the cloudiness essentially disappears if we pass excess of carbon dioxide through lime water solution. Apart from these, one can also pass the carbon dioxide gas through beryllium hydroxide solution, and that is going to again give us beryllium carbonate solution, carbonate precipitate, white precipitate of beryllium carbonate is going to form, and that also indicates, or that also can be used as a method for detection of carbon dioxide. So let us now also look at the method for preparation of carbon suboxide, that is C3O2. So the structure of C3O2 is this. It is also a linear compound, and this is the structure of C3O2, and we can easily predict that the method for preparation of this particular oxide has to again start with another if we start from malonic acid, and if we do dehydration of malonic acid, say by using P4O10 phosphorus pentoxide, then we will have carbon suboxide, because again because we have seen that when we did dehydration of formic acid, we could obtain carbon monoxide, and if we do dehydration of this malonic acid, then we will again obtain this carbon suboxide, and other suboxides or other higher oxides of uh, carbon, that is C5O2 as well as C12O9, can also be prepared by following similar strategy. So this essentially brings us to the end of this lecture. What we have discussed during this lecture are about different oxides of carbon. We have seen that there are two stable oxides of carbon. One is carbon monoxide and the other one is carbon dioxide, while there are three unstable oxides, that is C3O2, C5O2 as well as C12O9. Now we discussed about the chemistry of these oxides as well, and we initially looked at carbon monoxide, and we have seen that it is produced when one burns carbon in limited supply of oxygen, and it is also industrially prepared, or it is prepared in the laboratory as well by dehydration of formic acid using concentrated H2SO4. Then we also looked at how one can detect carbon monoxide, that is, one can use or pass when one passes carbon monoxide gas through an aqueous solution of palladium chloride. Palladium metal is going to be formed because carbon monoxide will reduce palladium chloride into palladium metal, and the palladium metal, because of its black color, can be easily identified, and this is how one can also detect the presence of carbon monoxide. Then we have also seen how one can estimate carbon monoxide quantitatively. That is, when one do reaction of I2O5 with carbon monoxide, molecular iodine is formed, and this molecular iodine can be titrated by using sodium thiosulfate solution, and that will essentially tell us the amount of carbon monoxide. Then we have also seen that carbon monoxide is a important industrial fuel, or it's a component of several industrially important fuels, that is water gas, producer gas, as well as coal gas. And we have looked at different methods for production of these water gas, producer gas, as well as coal gas. Apart from that, we also discussed the coordination chemistry of carbon monoxide. We have seen that it acts as a carbon monoxide can form stable complexes when metals are in low oxidation state, because carbon monoxide not only acts as a sigma donor, it also acts as a pi acceptor, because it can accept electron density in pi star molecular orbital of carbon monoxide, and that is why we call it as pi acceptor, or sometimes also as pi acid ligand, and that is how it can form stable complexes with metals in lower oxidation state. After that, we discussed about carbon dioxide. We have looked at different industrially important methods of production of carbon dioxide. Then we also looked at the important industrial applications of carbon dioxide, which is as a refrigerant, as well as precursor for urea, and also as fire extinguisher, propellant for aerosols, as well as we have also seen that learned that carbon dioxide is used as a uh, for inflating life jackets. Then after that, we have also discussed about the structure of carbon dioxide, which is linear in nature, and after that we discussed about the method of preparation of carbon suboxide, which we have seen that upon dehydration of malonic acid, one can prepare carbon suboxide, that is C3O2, and we have also discussed that other oxides of carbon, that is C5O2, as well as C12O9, can also be prepared by using similar strategy. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.